Greetings, salutations, all nice things. Welcome everyone to our next unit, which is trigonometry and non-right triangles. So last year with trigonometry, all the triangles that you worked with had right angles in them. And we used those ideas to generate things like the cast rule and how to look at angles beyond just acute angles. So this lesson, 5.1, is pretty much review. It's this idea of finding reference angles and identifying quadrants. But this concept of the cast rule is going to get used in a later lesson. So it is handy for us to review this. Also, given what emphasis trigonometry has in future years of study, it's probably a good idea to review this regardless. So you might find this lesson a bit more familiar, might more review-like, and that's okay, but it is really important that we make sure we solidify these concepts. Whenever we're dealing with a trig equation and we've isolated the trig function itself, our next step should in theory be to find the reference angle. And to find the reference angle, we'd use the inverse trig function on the positive version of the ratio. So whether this ratio given is positive or negative, we're going to stick a positive version in here. Since this is already positive 0.6, we're just going to keep it as positive 0.6. And when we do so, we'll now jump to calculator because this entire unit's going to be calculator based, FYI. And according to the calculator, this means that the reference angle is 36.870 degrees. So we know that's the reference angle, and then we can identify the quadrants as well, seeing as how this question does ask us to state the quadrants. And for that, we fire up cast rule. We note that the sine ratio is positive 0.6. The sine ratio is positive in quadrant 2, and quadrant 1. All are positive in quadrant 1, only sine is positive in quadrant 2. So we can say that theta is a component of quadrant 1 or quadrant 2. And that is that one. With the next one, we start off same way. We've got trig function equals some ratio. And we're going to find the reference angle. We're going to find lambda r. And to do that, again, we use the inverse function. We're using cos inverse. But we are not going to stick in here negative 0.15. Remember, to find the reference angle, we absolutely must use the positive version. If we don't, we're not going to get an acute angle and everything's going to go wrong. There are some people who made that particular oopsie poops on previous tests and stuff. So if that was you, now's a good chance to learn from it. Make sure you don't do it again. So for this reference angle, we put in positive 0.15 in the inverse function. We get a result from the calculator. Let's make my R look like an R here. And according to calculator, we get 81.373 degrees. So make sure you can get that exact same value. You can follow these steps. For the quadrant, the cosine ratio is negative, so we can't be in quadrant 1. All ratios are positive in quadrant 1. Can't be in quadrant 4, because cosine's positive in quadrant 4. Excuse me. So we're in quadrants 2 and 3. Oops. So those are the results there. Take a moment, do examples C and D. It should only really take you like a minute-ish to do so. If you need to pause the video quickly, and then move on. All right, I am proceeding ahead. Remember, we don't need to show these steps in pink. We have that nice color coding system to our notes. So for these next two, I'm just going to write only what needs to be shown, and that should be alpha. So the reference angle is the inverse tan of positive 4/3. You should be getting a reference angle 53.130. That is in degrees, so we'll keep that there. And we are in quadrants negative. We're looking at quadrants 2 and 4. And last one. Whoa, look at that error. I just got myself a variables error in the last question, apparently. That should not have been theta. That should have been lambda. Theta's a nice default, but that's not what was given in the question. So this one. Reference angle for beta is 75.522 degrees. And beta, that's the angle we're dealing with, can be in quadrant 1 or quadrant 4. That's those ones done. So we can take those to actually solve for values of the variable in these trig equations. We use the idea of getting the reference angle and then figuring out which quadrants we're in to determine what our actual angle has to be. In this next question, we're solving within one revolution. We can go from 0 degrees to 360 degrees. We'll start by finding the reference angle. So reference angle would be inverse sine of positive 0.7392. Putting that into calculator, we would get, this is apparently nearest tenth of a degree, so we'd get 47.7 degrees. That's the reference angle. We know, since sine ratio is negative, that we must be dealing with quadrant 2 or quadrant 3. And because of that, we're going to say that theta could be either the quadrant 2 version, so 47.7 shy of 180 degrees. Wait a second, what am I doing with my life? Reverse, not quadrant 2 and 3. Sine is negative. Quadrants 3 and 4. That makes way more sense. Whoa. So in quadrant 2, we're 47.7 more than 180. So 227.7. And quadrant 4, we are 47.7 shy of 360. So that's 312.3 degrees. Quick, try the next one. It should take you at most 90-ish seconds, maybe. And again, pause the video if you need to, but I'm going to go into it now. X. It's not a Greek letter, but we're still going to find the reference angle. Inverse cosine of 0.4549 gives us a reference angle of 62.9 degrees. In our head brains, we note that X must be in quadrant 1 or in quadrant 4, since we are dealing with a positive cosine ratio. Therefore, we must be looking at the quadrant 1 version, which is just the reference angle as is, Or quadrant 4 version, we'll take 360, we'll subtract 62.9, and we'll get 297.1 degrees. And that is that one, DUN, done. So we can solve other trig equations. Sorry. We can solve other trig equations where the trig ratio itself has not yet been isolated. We'll have to use our skills of solving linear or quadratic regular equations, non-trigonometric ones, in order to do so. Like over here, we've got this trig ratio, but it's being bothered by a couple pieces. There's this 2, and there's this 3. And just as we would solve something like, 3u plus 2 is 1.685, and solve that for u, we're going to solve for cosine alpha in the exact same way. Remember that you are allowed to parameterize if you want to. So you can say, let u equal cos alpha, and solve that way. If you find that easier, if you find it more direct, I would say do so. But if you are comfortable without parameterizing, then that's my recommendation. So I'm going to do these without parameterizing. I'm just going to say I'm going to subtract 2 from both sides and divide by 3. You don't have to show those steps. The ideas of subtracting 2 from both sides and the idea of taking whatever that is and dividing both sides by 3, those are not considered grade 11 skills. Those are not things you have to show. But if we subtract 2 from both sides and we divide both sides by 3, we will get that cosine of alpha is negative 0.105. And again, that's by subtracting 2 from both sides, and then after doing that, addressing this 3. From here, this is just like the previous page. We need to find the reference angle. So inverse cosine of positive 0.105 is 84.0 degrees. Cosine is negative. We must be in quadrants 2 and 3. Therefore, alpha must be the quadrant 2 version, so 180 minus 84. And 180 plus 84. That's that one. Take a minute, try the next one, see how it goes. Try without parameterizing. It's worth practicing these skills, even if they're new, if they're a bit challenging. Still get used to them so you can do things more efficiently. If you didn't pause, it's too late. Well, not really, you can still pause, but I'm just going to go to the next question now. This one you might want to take an intermediate step of moving things from side to side, like subtracting 6 sine beta from both sides. Note, if you do show it on one side, you do have to show it on the other to preserve balance. If you only show it on one side, then you're not showing the balancing of the equation. Therefore, that's incorrect from a communication standpoint. So make sure if you show it on one side here, that you show it on the other side as well. In any case, subtracting 6 sine beta from both sides gets us negative 3 sine beta. Adding 4 to both sides gets rid of the 4 from the left, leaves us with positive 2 on the right. So, sine beta is negative 2/3, which means that the reference angle is inverse sine of positive 2/3. Calculator says that's 41.8 degrees. Our answer must be wherever sine is negative. The sine ratio is negative when we are dealing with quadrants 3 and 4. So beta itself, the angle can be the quadrant 3 version. or it can be the quadrant 4 version. So that's those ones. Not so bad with linear trigonometric equations. It's kind of easy to move the pieces around. With quadratic ones, it does require you to be able to factor skillfully. Now again, if you want to parameterize this, if you want to say, let u equal sine theta, and then deal with 3u squared plus 4u minus 4 equals 0, feel free to do so, go for it. Just note it will be less efficient. My recommendation is put all these let statements and whatnot on a scrap paper, factor on that scrap paper, and let that tell you how to factor this particular expression on the left here. And again, I'm going to do this without parameterizing. If we had 3u squared plus 4u minus 4, then that would factor as something like probably 3u and u, probably looking at positive 2, negative 2. So that's what I'm going to do over here. I guess I technically did just parameterize, but I would have done that on scrappy 2 paper. So in my actual work, we put what that would be, but replace the u's with sine thetas. Again, it's 3 sine theta and sine theta. That's how we'll get 3 sine squared theta. And then we need negative 2 and positive 2 there. That ensures that our outside product is 6 sine theta. Our inside product is negative 2 sine theta. That gives us the 4 sine theta in the middle that we're after. So that's all good. This line is almost super perfect. It just has a communication error. This is an expression because there's no equal sign. We still need that right side to be there the whole way through. So this equals 0. Don't lose that part. Don't turn the equation into an expression. That's a big no-no. From this, we get 2 possibilities. One possibility from this one is that sine theta is 2 over 3. And from this one, we get that sine theta is negative 2. We know that sine theta, sine and cosine are restricted to be between negative 1 and positive 1. So this right here has no solution. We can't go like this. That's not how we indicate no solution. We do actually need to write that for this particular equation, there is no solution. For the other one, we'll find the reference angle, which is just like the previous one, right? Positive 2/3. So 41.8 is our reference angle. Therefore, for this equation as a whole, it's only this left branch that we need to be concerned with. The right branch gave us nothing. So for that left branch, we're dealing with quadrants 1 and 2. So quadrant 1, 41.8 degrees, and quadrant 2, 138.2 degrees. Take a moment, try the next one. I really encourage you to try it without parameterizing. See if you can factor without doing the parameterization method. If you need to, then in a test or quiz situation, that's something you can rely on. But you need to try it to see what you need to do to be successful with it. So take a moment, pause the video if you need to, and go ahead. And it's me. Hopefully you tried this already. If you were able to factor this successfully, you probably had a 2 tan x in one of the brackets and a 1 tan x in the other set of brackets, and that equals 0. I need a 3 and a 2 in here. I need to total negative 5x. So that's a minus 3 there. That's positive 1 because outside product negative 6 tan x, inside product positive 1 tan x, total is negative 5 tan x. So I'm all good to go there. Two possible scenarios. Tan x could be negative 1/2, or tan x could be positive 3. You might be tempted to say this one has no solution because, whoop, 3 is more than 1. But we are dealing with tan here. Tan doesn't have that same restriction. You can have the opposite side be 3 times the length of the adjacent side. That's okay. So this one does have a solution. So for each one of these, we're going to find the reference angle, and we're going to find its related angles. For the first one, if tan x is negative 1/2, the reference angle is inverse tan of positive 1/2, which gets us 26.6 degrees. Tan is negative there, so we're dealing with quadrants 2 and 4. In quadrant 2, we're talking about 153.4 degrees. And in quadrant 4, 333.4 degrees. I'm not closing this bracket yet. I'm not done with the other branch. So I'm just going to leave those there. Those are the results from this particular branch. I'm going to get the results from the other one in there as well. So if tan x is equal to 3, the reference angle will be inverse tan of 3. That gets me 71.6 degrees. Since tan x is positive 3, we're dealing with quadrants 1 and 3 in that case. So quadrant 1 version of this reference angle is 71.6 degrees. And the quadrant 3 version is 251.6 degrees. And now that one's done. So the order we write these in doesn't really matter. We're in set notation. This is just a collection. You're laying out your trophies in your trophy case. Doesn't really matter what's put where as long as they're all accounted for. So this question is done. I encourage you to work on the practice work. And that's about that. I'll see you when this voice sounds a bit better. Be good to yourselves, be good to one another, and do math forever. Amen.